We are going to start the heat and thermodynamics. In the part of the heat and thermodynamics, today we are starting that basics in thermodynamics here. See, first come to the heat, the basics here, temperature. See, in our daily life, the heat and temperature, this is a common part of our life. If we rub our hands, temperature will come. Our heat, temperature, hands will warm up. If you are seeing this, suppose if any block, it moves on the rough horizontal surface, it be getting warm up. Suppose two vehicles, if they are collided each other, then what happens is they will get it heated. Suppose if you are moving on bicycle, see, if you are rubbing your shoes with the floor, what happens that the bicycle speed slowly getting down, your shoes will get warm up. In all the process, what happens is that the mechanical energy vanishes up and heat will be generated. Here, the cold bodies will absorb the heat, whereas hot bodies, what happens that it loses the heat. See here, this temperature, come to the temperature here, is nothing but a degree of hotness or coldness. If you observe this, let this particular body here, this is the body here, is a body A here, is a body B here. Whenever it's having the more temperature, we are considering this is a body, hot body. And whenever you are considering B here, let the temperature TA here is the temperature TB. Our assumption is TA is greater than TB. So it's considered to be a hot body, it considered to be the cold body. If both are in contact with each other, provided there is no mechanical energy lost, definitely what happens that of some time this hot body, what happens, it loses the temperature, and cold body, it absorbs the temperature. But resultantly what happens that heat can be transferred from this body to this body without involve any mechanical energy loss. So that's what, how can we define that heat here? It's a transfer of internal energy from a hot body to the cold body without involve any mechanical energy process. See here, if you consider the temperature here, it's a measure of degree of hotness or coldness. In this class, first we will to discuss about how to measure the temperature. See, if you observe this, the temperature, the process of measuring of this temperature, we are calling as thermometry. How can you measure the temperature? If you are getting fever, how can we measure our temperature? By taking thermometer, we will measure our temperature. So that's what this thermometry, in this case, how to measure the temperature based on what happens that it measured by the variation of this basic property. This property, if you take that thermometer, what happens that how that particular mercury that can be expanded. If you go for resistance thermometer, how the resistance varies with the temperature. If you are going with your pressure thermometers, how the pressures varies with the temperature. If you are going with the volume thermometer, how the volume can be varies with the temperature. So here this basic property that depends upon the temperature. Say, if one thermometer we are using resistance as a basic thermometer, one thermometer we are using the pressure as the basic one thermometer we are taking the volume thermometer. We have a doubt why we are going for different properties rather than selecting only one property here. See here, we don't have unique property which varies linearly with all ranges of temperature. Hence, whatever the requirements we have, that chooses, we are choosing that particular requirements so that we can choose that particular thermometers. See, in all the properties, that's a property is common that let X is the basic property, it varies with temperature, so I am writing that T is equal to X plus B here. In the old process, old and thermometry process, here what happens that they are taking temperature initially at 0 degrees centigrade, and what happens that finally they are taking that 100 degrees centigrade. Here X is our basic property here. Once again I am stressing that this basic property may be the resistor, may be the pressure, may be the value, that depends upon our requirement. Here if you are observing 0, if you are taking the 0 as our temperature, initial temperature, I am writing some 0 degrees centigrade, some A x naught plus B here. here I am taking that 100 degree centigrade another temperature, I am taking the property at 100 degree centigrade plus B here. I am taking general temperature T is equal AXT plus B here. If we are writing this, see here, if T minus 100 I am taking this equation minus this one. So, I am writing AXT plus B minus AX100 minus B plus B here by I am taking 100 minus 0 here. See, T is equal AXT plus B here minus 100 here. What I am writing that AX100 plus B here, 100 minus 0 here, AX100 plus B minus what about this one, AX0 plus B here. See, T minus 100 by 100 here, what happens that AXT plus B minus AX100 minus B by AX100 plus B minus AX0 minus B here is getting cancelled. See, A is a common, that XT minus X100 by A is a common, X100 minus X0. This can be T minus 100 by 100. See, A gets cancelled. See, T minus 100, we are taking that XT minus X100 by X100 minus X0. See, if you observe this, by taking these values, this is the property at T temperature, this is the property at 100 degree centigrade, this is the property at 0 degree centigrade, we are measuring this temperature T. This is the Wolfram thermometry. Here, what is the drawbacks of this thermometry here? We are taking 0 degree centigrade and 100 degree centigrade. There, one is at we are calling as ice point, and one more is what we are calling as boiling point. So, these points are not constant, because as the pressure varies, definitely what happens that pressure, these values will vary. So, hence we go for Morton thermometry. In that Morton thermometry, we define this temperature can be equivalent to this triple points, like absolute temperature. So, initially what happens that our limits are 0 degree centigrade and 100 degree centigrade in the Wolfram thermometry, whereas in the Morton thermometry we are taking as 0 Kelvin and 100 Kelvin here. Here, if you observe this, this is at 0 degree Kelvin, what happens that your basic property X, whatever the basic property, that is resistance, pressure, volume, that tends to 0 at 0 Kelvin here. See, if I am taking that at 0 Kelvin, T is equal to K here, AX plus B here, this will be what happens that this property will be 0 plus B. So, we can directly write down B is equal to 0 if we are taking that Morton thermometry. If you are taking that 100 degree centigrade, 100 degree Kelvin, so 100 K is equal AX 100 plus already we know this B is equal to 0 here. So, here if you are taking these equations, what we are getting this at temperature T is equal at triple point XTR here. So, T by 100 is equal XTR by X 100. So, T is equal XTR by X 100 into 100 kilo. So, this way we are measuring that temperature by using the Morton thermometry. See, here if we are taking this next one, so measuring the temperature is over by using thermometry. Next, expansion of materials. We have three materials, one is solids, next liquids and gases. See, as the intermolecular forces are very large in magnitude for the solids, that's what their expansion is minimum in the case of solids, whereas intermolecular force is very, very less, so this expansion is more in the gases. First, we will start with how the solids can be expanded. Solids, if I am taking the three steps, one is it's a linear form, one is a aerial, like it constrains only the length here, and now it will be constrained with area, and one more with cube. Let at temperature T1 degree centigrade, initially length L1 here, T2 degree centigrade, its length will be L2 here. See, as the temperature increases, its length varies. Provided T2 is greater than T1, so its length is increases compared to the L1. So the change in length L2 minus L1 is directly proportional to initial length, and again it's directly proportional to the temperature difference T2 minus T1. See, L2 minus L1 is directly proportional to what we can write down L1 into T2 minus T1. If we are defining one constant, that is L2 minus L1 is equal alpha into L1 into T2 minus T1. So, alpha is equal L2 minus L1 by L1 into T2 minus T1. So, we are writing this alpha is equal, this is change in length, I am writing some delta L by L, this is the delta T here. This alpha we define for the particular solid in the form of metal rod. So, alpha is called what we are calling as coefficient of linear expansion of solid. If we are writing the same for the metal plate, how can we write down this? See, this is a metal plate here, initially T1 degree centigrade, whatever that initial area is A1, T2 degree centigrade area A2, the change in area here A2 minus A1 is directly proportional to A1, is again directly proportional to T2 minus T1. So, finally, A2 minus A1 is equal one constant we are calling as beta into A1 into T2 minus T1. So, beta is equal, what is that, A2 minus A1 by A1 into T2 minus T1. So, we are writing beta is equal delta A by A into initial length into delta T here. This is initial length, this is initial area. Similarly, for the cube, what happens that we are taking that gamma here, delta V by V into delta T. Now, the relation between this alpha, beta, gamma we are going to discuss now. Provided this is the rectangular plate, it is length L here, it is the breadth here, area we know this length into breadth here. I am applying that approximations, delta A by A is equal to what we can write down delta L by L plus delta B by B. If I am taking delta A by A into delta T here, this can be delta L by L into delta T plus delta B by B into delta T here. See, already we are defining this will be previously beta here, this will be some alpha 1 because delta L by L here, this is alpha 2. So, this is coefficient of expansion of this particular rectangular plate along the length, this is coefficient of expansion along the breadth here. Suppose if the material, if it will have the same expansion coefficients on along the length and breadth, we are writing alpha 1 is equal to alpha, that can be equal to alpha, then what we can write down alpha plus alpha, this can be 2 alpha. This is the relation between beta and 2 alpha. Suppose if you are going for the cube, same, so L here, this is that breadth here, this is H here, volume is equal LBH. If I am writing this, delta V by V is equal delta L by L plus delta V by V plus delta H by H. If I again divided by this delta T here, this can be delta L into delta T plus delta V by V into delta T plus delta H by H into delta T here. See, we are writing this is about the gamma, this is about alpha 1, this is about alpha 2, this is about alpha 3. Just now what we discussed, this is alpha 1 and alpha 2 here, alpha 1, alpha 2 and alpha 3. Another factor comes that this is along that height. See here, if this particular cube, they will have complete expansion coefficients, alpha 1 along the length, alpha 2 along the breadth, alpha 3 the height. If they have same coefficient of expansion in all the sides, then we can write down alpha 1 is equal, alpha 2 is equal, alpha 3, that can be equal to alpha. So gamma is equal 3 alpha. This is about expansion of solids. One is we are defining this alpha here and beta here and gamma here.